Well, anyway, thanks for coming. It's going to end up with the database. This is a double act, so I'm going to take 20 minutes of your valuable time, and then Heinz is going to come in and do the final section. Hopefully I can make it all the way through in the onesie. But before you're asking, why am I in a onesie, because some of you that are observant have probably noticed, this is the official outfit of DalmatinerDB. It's got spots all over it. Dalmatiner is a word you probably can't spell or pronounce, but it's the German word for Dalmatian. And Heinz picked that word for the database because it's a dog with a lot of spots, lots of little points in the database. That was the reasoning behind it anyway. And I work for a company called Dataloop, and we use it. I'm not an Erlang developer, believe it or not. My background is a sysadmin. I pretty much, that was me about 10, 15 years ago. I used to just sit at a desk. People would ring me up and ask me how to fix things, and I would say, turn it off and on again. And I got quite good at turning things off and on again, to the point where I wrote lots of automation to turn stuff off and on. So they call it DevOps nowadays, but back then it was just Python and Bash and other weird stuff. So I'm going to tell you the story of how I became enlightened and started to use Erlang and ultimately Heinz's software. So in 2013, or at the end of 2013, a series of life choices had led me to launch Alfresco's cloud product. This was about the, sorry, this is getting very hot. This is about the, I don't know, the 6th or 7th time I'd launched a SaaS product for some other company. And at that particular time, like any DevOps person, I was doing one of two things repeatedly. I was either helping people deploy software or helping them monitor and measure it. And I found myself at the end of a 3-year gig at Alfresco, helping them launch their SaaS product, which was an online document management system. You could upload files. It was very sexy. But I got a bit bored of that stuff. Do any of you guys recognize any of those logos? Do you know anything about Nagios or StatsD or Graphite or all that sort of stuff? So basically, what I was doing was what I'd done 6 or 7 times before, putting together the kit car of rubbish. People's half-completed hobby projects, they'd stuff up on GitHub. I'd take them like they were gospel, fit them together in weird and wonderful ways, and before you knew it, you had like a Franken monitor, or the kit car, which is what I used to call it. And I'd done that loads of times, and I thought, I need to make a choice now. What am I doing next? The choice basically was either go consulting, where I could have been wonderfully happy. I could have billed for £20,000 a month easily. Lived a wonderful life. Or go and live an impoverished life as a person doing a startup and end up in a onesie, which is where I am in life at the moment. So obviously, never been very good with decisions. Decided to actually go ahead and do the startup. So that was 3 years ago now. Started a company called Dataloop. The idea would be it was going to be all things to all men. Unbounded scope. We were going to take all of that kit car of monitoring tools and actually do it properly in a single app. We'd take the Nagios that would do the polling, that big binary that would run check scripts on remote hosts that would let you know if things were up and down. It would be the things that developers could use to shovel metrics in and you could see pretty graphs. And it would be the one place that you went to. So we started off with I think a fairly narrow spec, which was, let's tell people when things are up and down, which is what you can do in Nagios. Let's get some pretty dashboards. Let's do some alerts. We had some ideas around adoption. I've always been a fairly lazy person through my entire career. I mean, the only reason I learned to program was to make sure that I never had to do any work. So I would just program things. The computers would do it for me, and I could sit back and do other things. So that's what DevOps is, basically. We thought that we could build a system where we could entice developers to do most of our work for us. They call it self-service nowadays. So the idea would be that we would have a platform, we could give it to anybody in the entire company, and they could write their own custom monitoring scripts, they could instrument their own applications, and they could get it all into a single place, and we put enterprisey stuff and secret sauce in there as well, just to make it all work. So with that in mind, we went off and started building it. We got better at architecture diagrams later on. This is a very early one. But you'll see there are a few Erlang bits in there. There's a bit of a hint that we were going to go in that direction. We started off for the first year pretty much working on our agent. So the idea was to make it very, very simple. We built an agent in Python. We've got it rolled out via config management to all these different boxes. It would spin up, start a WebSocket connection back to us as a SaaS service, and we'd have bidirectional communication, and we could push down scripts to the boxes like you did with Nagios, except it would be simpler. And also we'd have a port where you could get data being shoveled in. So that's what, I'm scared of touching that actually. That's what that bit is there. That's our Dataloop agents connecting in to an exchange. That's all written in Node.js. In fact, most of it was. We call it a prototype, but at the time we really meant it. And this is where the third-party agents would come in and push all of the metrics in. All of this stuff in the middle is all Node.js, all talking to RabbitMQ, so lots of Erlang in that. Somebody decided to put MongoDB in there. We were naive at that stage. It's Colin there, he did it. And at the time we were using Riak, so we never wanted to build a time series database, so I'm not entirely sure why I'm here. But we decided we were just going to have the minimum functions. We'd just have key values, and we would forego any of the crazy analytics stuff just to get the product working. So we'd get all the agents connecting in, sending in time series data, and we could create dashboards and alert rules and actually get the product release. And then we'd do the hard bit later, because who wants to do the hard bit first? So that was where that was. This took about a year. We managed to convince a couple of companies to buy this. This didn't exist, but they bought it anyway. And then we started to build it behind the scenes. And it was all working pretty well when we just had a couple of companies on it. Then what happened was we launched, which I was against, to be honest, but we did it anyway. And things went well. I mean, for a company, we started to, we make our money by selling agents. So agents would get installed across machines. We'd get a few dollars per agent for every agent that gets installed. So we really like it when people take our software and roll it out. It's like cha-ching every month. It's pretty cool. We did that. This is the whole of 2015. What you'll see there is, started off, nobody really cared. That's what always happens when you launch a product. You put it out there and people are like, I don't really care about this. And then we managed to convince a few people to try it. And then what happened with that blue line there, that massive one, was we made a couple of sales and immediately a few thousand machines just got dumped on the system overnight, which we didn't really anticipate. What really happened was it all caught fire. Like the whole thing exploded. We managed to, it would be nice just to get a few of these things on there. Luckily, we managed to hide it, like any good SaaS service. As soon as it caught fire, all of us behind the scenes were bailing out, putting water on it, doing various crazy things. So for 4 months, we had a very, very hard time. We tried not to put any more new users on the system. Although we were actively selling it, we were also actively deferring people to try to move them off. And that's particularly where the fire is. So if you guys can see that where the flames are, that was the problem areas. We had issues basically with our Node.js workers mostly. They seem to be a bit unbounded. You'd run this big event loop thing. They would pretty much pull everything they could off of the queue and go sideways forever, like a big IOU system. I promised to do this at some point, and then it'd fill up to like a gig of memory and then crash, which is okay because it'd start again. But we got a bit fed up with trying to tune all of these Node.js workers and fighting all that stuff. So we did what every company does when the problem gets hard. We put Redis in the middle. And that saved us. That was enough to buy us some time to fix it properly. So yeah, the metric workers would pull metrics off of the queue. They'd put them into Redis, which is massively fast. Even we couldn't outpace that at the time. And then another set of workers would take it off of Redis, put it into our database, but it would batch up the metrics. So that's the kind of, Heinz will go on about this, we kind of cheated. It's hard to do like an oscilloscope of maximums and minimums in a database when you're writing. If you can batch them all up and then sort of play them at a fairly low rate, that's over a period of time, that's much easier. So yeah, our Node.js workers weren't scaling. We had big memory management issues. we had big physical eight core boxes, so we were running 8 Node.js processes on those boxes, 1 per core. What you'd find would happen was we had to put some cache inside the Node.js stuff, but the memory management wasn't brilliant. You only had about a gigabyte of memory to play with. If a Node.js process ever gets above 1.5 gigs, that's the end of it. You have to shoot it in the head and get a new one. We had big caches. If it got up to over a gig, it would do weird garbage collection things over and over. And then we'd be doing crazy things then with flame charts, trying to work out what it was causing the garbage collection. It wasn't a great situation to be in. I hope you can't read some of those words; they're a bit rude. But we went through a comparison of different languages because we realized probably needed a bit of a fundamental change. Sticking Redis in was one thing, but the problem was in the workers. We probably need something more applicable. We looked at Java. That's the one crossed out. I think people generally agree Java was a bit depressing. They would prefer not to ever have to touch Java again because they'd done it at the last jobs. C, they looked at. Colin told me if we went with C, we'd need at least 5 times as many developers to write all the code. And we actually tested Go with Hecker, which looked quite good at the time, but they seem to have discontinued it now. And in the end, the Erlang stuff won out for us because you could actually see what it was doing live in production. And it seemed like the sort of thing that it was more scientific. We would look at Node.js and you'd end up with some problems. You just go, oh, it's just like that. We wanted to end up in a situation where you could actually look inside and say it's doing that because of this, and not end up in Wonderland. About 6 weeks later from the initial, let's take this particular metric service, to having not touched an Erlang book, having read it, I think Thomas picked it up in a few weeks, rewrote that worker so it did the same thing in Erlang. No more crashes, much more fault tolerant, reduced the number of boxes in half, so that was quite good. And then we came to sort of the final bit of the puzzle. We're kind of committed now to rewriting all of our Node.js backend stuff in Erlang to make it more fault tolerant and make it faster and easier to troubleshoot. But we still wanted to remove Redis. We didn't really want to have that single point of failure or to have to build a load of sharding on top of Redis so that we could have many of them. You still get like a bit of a gap if you lose a Redis box. So what we did was we decided we quite liked Riak. We didn't necessarily want to build our own database, but we started looking around at different options. InfluxDB at the time was pretty immature. It didn't really do clustering. When it did do clustering, it only clustered to a size of 3, which wouldn't have been any good for us, I don't think. We didn't want to have just 3. And then there were other ones based on Cassandra, OpenTSDB. If you've ever run Hadoop, I never want to run Hadoop, really. So we looked around. The guys had this idea of, there was a bit inside Riak that was quite good, like the Riak Core bit that did the ring and the distribution. And we quite fancied the idea of building a very thin layer on top of that. And then we found online through an internet search that somebody was crazy enough to have already done it, although he'd hidden it behind a name that nobody can say or even search, which was lucky for us because it hadn't been acquired by a VC and cost lots of money. So we found this repo, we started to commit to it, and yeah, this is basically the story of DalmatinerDB, getting rid of Redis, having a decent metric store that's very fast so that we can just write metrics off the queue directly into it. Something that we can add features to that isn't a massive product that we can actually iterate on for our particular use case. And that was one of the other things. That deferring of those advanced fancy features was catching up with us. There's only so long you can delay the inevitable with developers wanting features. Operations are happy. Like, you give them a web interface that's slightly better than Nagios, they love it. But as soon as you start giving a developer an interface and it's not quite amazing, then they won't use your product. So we want all those cool features. So we got Erlang solutions in. That was kind of one of the projects that we kicked off. We had a team of 3 people on the back end that were quite keen on using Erlang. We wanted to fast ramp them up, so we got Erlang solutions to sit on site with them. We kind of trained them. We started working with them on the database and the workers and other things. Heinz came in and started to do some consultancy as well. We got rid of Redis. We reduced the number of metrics workers again now down to a piddly little amount. It's gone up again, unfortunately. We got more customers, but it seems to be a never-ending battle. But yeah, new metrics worker directly into the dog this time. no Redis in the middle. And then we started adding, well, analytics features. So when we first met Heinz, it was pretty much a graphite replacement, which meant it had dotted metric paths. You just had a hierarchy that you encoded. It works very well if you're clever and know every answer up front. If you've already got it solved and sussed out in your head, it's a brilliant solution. You definitely don't need metrics dimensions at that point. Most people start off with a thing to measure, and then over time will want to decorate it with tags like, this is a production metric, this is in US East 1. You want to do the where clause, that's the cool bit. So we worked with Heinz on adding Postgres as an indexer to it. So all of the metrics would get written into the database, but we'd also, the first time we saw a particular dimension, we'd write it into Postgres as well, so that you could do these fancy analytics things. You could take, from my production cluster, where it's an application server in production, select one of my time series, like my New Relic, throughput, and then you can do really complicated, like graphing calculator type things on them, combine series together, sum them up, derivate them, transform them, and do loads of weird things that I never needed to do as an operations person, but apparently are absolutely required as a developer, which is more where we were heading. And you can do other things like time shift them. What's my the number of visitors on the site divided by the number of items purchased, and then shift it back 24 hours and overlay it so that you can see yesterday's purchases versus today. You can do all of that. We cheated again on the front end, so the back end kind of skipped ahead and got a lot of features. Dataloop itself, we only had a single developer at the time on the front end. We've got more now, but we kind of cheated by adding the Grafana interface onto Dataloop so that you could do all of these functions and we could test it all. Now that's kind of being written and pushed in. But yeah, this is all kind of, and the most important thing is we contributed all of this back. So we didn't just take it like a lot of software companies do and kind of use it internally. Everything that we've done here, we pushed back into Heinz's repo. It's free. We package it up. You can, with a very short installation guide, install a few Debian packages, get it running on your server, and you get what we're running behind the scenes in Dataloop. It's probably overkill unless you're running a SaaS business, but it is quite cool. And you get all of these fancy features in the app as well. Where I normally get heckled, because databases are one of those weird topics where people like to hate on your opinion. I can come up here and say how good it is, and somebody go, have you tried Kairos DB? Or have you tried Influx? Or why didn't you try this? This is brilliant. I got fed up with that. So we tested every single one, and they're all rubbish. So they're all. We did a massive blog post on it. We've got the world's biggest Excel spreadsheet. It's got about 40 different factors that we took into account. They're not all rubbish. Some of them do things quite well. If you've got a different use case, like you don't necessarily want to run a distributed system, there are single Go binaries that you can run in certain cases. If you've already got Hadoop stacks, it's probably the onesie, isn't it? The curse of the onesie. But yeah, this will be in the presentation. You can look at it, you can agree or disagree, but it's factual, and we've tested all of it. We think that for our use case, Dalmatiner is pretty good and it's very fast. So we get about 3 million metrics per second on a single node box. And Heinz will go into, I'm not allowed to ruin that, but yeah, have a look at that. We got better at architecture diagrams over the years, but this is sort of, it changes every day because we keep adding new services in production. But we're still using RabbitMQ 3 years later. That's still how we push all of our data around. It's like an event bus. It's where we push metrics as well. We've still got the ways of getting metrics in, although now we support dimensions, so we support Nagios and Graphite, but also Prometheus and InfluxDB metrics can be pushed in as well. We're heavily reliant upon Dalmatiner with the Postgres indexer, so you can do all those crazy analytics features. And a lot of our services now are in Erlang, and are, if they're not, they're being ported over. We're still, for any new stuff, we still tend to prototype it in Node.js very quickly, get it working, and then immediately rewrite it once it's kind of in and working. It seems to work out well that way. That's it. We're pretty happy. We're hiring as well. If you want to be the one wearing the onesie, you can come and join Dataloop. It's probably not much of an advert, is it? But yeah, things are pretty good. We're a big Erlang, obviously, advocate, so we'd like to get some more Erlang people in there. And now over to Heinz.
Hello? Wonderful. Okay, I want to talk a bit about DalmatinerDB, and I will not go into the technical details because that would take about 2 or 3 hours. And for those interested, I'll be here the next 2 days. Just come up and we can talk. So I want to tell you this story how Dalmatiner came to be, because it's an interesting story. The whole thing started about 2 years ago on the day. Well, actually 2 weeks earlier. What I usually do when I don't write databases is I have developed a cloud orchestration system which lets you set up your own private or public cloud, manage a ton of hypervisors and virtual machines. One of the requirements a customer had was we want to collect metrics for all the hypervisors, all the VMs, store them in a second precision forever. And they had over 100 hypervisors in 3 data centers, and I don't know how many virtual machines at that point. So they wanted to measure everything. Anyone used Illumos here? No, okay. So there's this wonderful tool called KStat, which gives you kernel statistics on literally everything. And it ended up being about 1,000 metrics every second per virtual machine. Plus another, let's call it 2,000 for the hypervisor itself. Which quickly sums up if you want to push this every minute. So I went out and tried to find different solutions, starting out with a pretty small subset of the metrics involved for about 2,500 in a test system. And I tried InfluxDB, which blew up at about 3,000. I tried Graphite, which blew up at about 7,000. I tried KairosDB, which handled the 25,000 with about 60 gigabytes of memory and 2 to 3 seconds response times to queries, which wasn't great. And then 2 weeks later, I happened to be in Stockholm at the Erlang user conference. And one of the great things that usually happens here is you meet really smart people. So I had this crazy idea. You could just store this in a file. And I talked to someone who I greatly respect who was here that day, and sadly isn't today. I don't think he actually knows that it's his fault that I started this. Whoever knows Darach Ennis, he is like Erlang guy and does a lot of performance work. A brilliant and really nice person. And I talked to him about it, and he said, yes, that could work. And then there was a point where I decided I'll just give it a try. If that smart guy thinks it can work, then it has to work. It turns out it does. So, as I thought about it, thought about the problems, and I am of the opinion that algorithms beat execution speed. So I went with the language everyone tells us is slow. I'm pretty sure everyone here has heard Erlang is too slow once or twice in their lifetime. And I don't think Erlang is too slow. I think algorithms are slow in the worst case. So at this point, I found this yesterday. I had to put it in here. It's a little snippet of code where people apparently thinking that execution speed matters the most, so it's a go and go as fast, so we don't have to think. So what happens here is they calculate some statistics, the sum of a set of metrics, the mean of a set of metrics, and the count of a set of metrics. And I hope I really understand what the mean is, because I'm really scared that this actually makes sense, because it looks so stupid to me that it's scary. So instead of just dividing the sum by the count at the end of this, they do some tricky math with multiplying the former mean with the former count, add the new one, and then divide it by the count plus 1, and then increment the count. This is just people not thinking. And that happens if you are in a language which is supposed to be fast. You don't think about the algorithm. You're like, oh, this is fast. And that is how it came to be, and it works really well. So I went out to reinvent the wheel because there are a million databases, and I wanted to do it without reinventing the wheel because I'm utterly a lazy person. I think that's a personality trait we share. It's one of the few, I hope. So I figured, what all can I avoid doing? So I figured I'm running on Illumos, which is a Solaris derivative, so I can use ZFS, so I don't have to really care about compressing the data. The data file system does this for me. It does it better than I could ever do because those are smart people, I am not. Same goes for checksumming the data. I don't have to care about integrity of my file because the file system guarantees me. My file is either I get an error back or it's correct. I don't have to care about snapshotting and this stuff because my file system gives it to me. It's all work I could avoid. I was really happy about not doing that work. Distribution. You can't expect to handle the load I was seeing there without going to distribute your system out. A single box can handle a lot of metrics, and he spoiled it. But you can't go just scale horizontally, vertically. You have to scale horizontally at a point. And this brilliant people at Basho, which again are pretty much a lot smarter than me, solved this problem. They released Riak Core, which is amazing. You get the distribution, you get the cluster management, it gets scaling, it works wonderful. You get the whole CLI, which lets you manage your cluster, add stuff, and they even documented it, so I can tell him when he annoys me, just look at the Basho things, it's the same. It's wonderful. Another thing I didn't have to do. And then this annoying bastard came up with dimensions, which is utterly stupid because, as you said, smart people can just make up the path and be good with it. No, don't tell him I said so. It's actually pretty cool. I didn't want to write an index. I don't want to do queries which is like where A is equal B and or blah, blah, blah. But there's Postgres, and it's amazingly fast for this stuff. So why not outsource a problem to someone who's good at it? So dimensions just go in Postgres, and normal SQL queries can be executed to resolve dimensions. Blazingly fast, and I guarantee you a lot faster than I could have ever done. Works wonderfully. So there was one thing which wasn't solved for me, and that is the data layout on disk. But again, I borrowed from someone who had done it before. I borrowed from Graphite. They have this simple Whisper, I think it's called. Flat files. Works wonderful. And if you think a bit about it, if the data is in an array on the disk, you had sequential reads and writes for everything, and they are just faster than looking up, transversing a tree or something like that. And the wonderful thing is, ZFS has this caching. It's called ARC, which is an amazing cache that does effectively what you would do with memory map files, just a lot better because it knows about the file system and the files. So it will read the stuff ahead of time. If you need it, it will keep them in the memory. It will keep them if you want in a SSD second layer. It's awesome. Looking at the compression, it turned out that if you store a 64-bit value for each point in time, it compresses down to 1 byte in not necessarily the average, but in most cases. There are some outliers where it goes higher. There are some outliers where it's lower. But around 1 byte is really, really good. And since I'm lazy and I don't want to do complex stuff, it's as simple as it possibly gets. Reading the 60th 64-byte value in a file to get the 60th value in your data is really simple. There's not much I can do wrong. I'm really good at doing stuff wrong, but not even I can do that. So this is just a lot of stuff I hadn't to do. Pretty much it's a database I didn't do. And I want to actually encourage everyone when you build something to try to be as lazy as me. Because 90% of the time, someone has done it before. Perhaps not to 100% of what you want to do, but perhaps 95%. And perhaps those 95% are so good because they have been around for a few years that the 5% extra you could get when you do it yourself doesn't make a difference. So if anything you take with you today, other than seeing this dude in a Dalmatiner costume, then let it be try to look if someone did it before and use their stuff instead of reinventing the wheel. What? Oh, 10 minutes. Oh, that's wonderful. The second thing that obviously had to be done from scratch is the query engine. It's a SQL-like syntax, a bit adjusted for time series, as time is always the main querying factor. It is a streaming query engine, which gives you the advantage that if you compute over large quantities of time, you can start getting results very quickly and keep the system busy doing computations while you wait on reads, for example. And if you read multiple metrics at one time, you can do the calculation on the first while the second gets fetched. So you very effectively end up using your CPU time, using your memory. And you would think that sending messages during the query processing is slow, but it's amazingly fast in Erlang. It is really, really good. So, serverless infrastructure, my ass. No, that didn't work. Let me try this again. Oh, yeah, here we go. I don't know what went wrong. Serverless infrastructure, I think my assumption is we are talking about informed decisions regarding state and its location. That was better. So DalmatinerDB is very strictly divided into stateless and stateful components. And when I say stateless, I don't see configuration as a state in this case because it's configuration state, not application state. So bear with me and accept that stateless is okay if there's a configuration file. The front end is entirely stateless. There is no data stored in the front end. It just goes over the network, grabs the raw data from the database, and does a computation. The proxy, which you haven't heard about until now, is also stateless. The proxy takes in a variety of different protocols like OpenTSTB, Influx, Graphite, Matrix 2.0, and some other one I forgot, and translates them into something that DalmatinerDB understands, which is awesome since you can just take your existing system and point it there and the metrics get stored in a much faster database. So those are stateless. They don't need to keep state, which makes them simple. You spin them up if you need more. You shut them down if you don't need them. And then you have two stateful components. You have Postgres, the indexer, and you have DalmatinerDB, the database. And both only serve really the purpose of keeping the state. They don't do computations. They don't do fancy stuff. They are just a state. And that makes them really easy because they don't do much either. They just do their one thing, indexing for Postgres, storing metrics, reading and writing them for Dalmatiner. So combining them, it turns out the methodology, whatever this word is, I choose worked out pretty well. Might be an accident. There's a very small API between these components. And this API is very, very stable. It has changed once in the last 2 years, only to add compression. Please see the difference between an external API which the user has and an internal API which is between the services. The interesting part here is that when we did the stuff with the dimensions, we didn't need to change the database at all. The database remained untouched and running while the dimensions were added. They only were added in the proxy to write them and in the query engine to query them. The query engine could keep going to the old backend without any change. And that was really, really, really nice seeing that. A lot of changes we did, we entirely changed out the query engine. Didn't matter because the protocol stayed the same. You had a separation between stateless and stateful. Wonderful. There was barely any downtimes ever, I think, because of changes, since they only were in the stateless components. The logic is there. The stateful components which served for ingress and egress remained the same, no downtime. So this is another nice trick I learned during doing this. I would totally do it again for my next application. And if anyone builds something, think about doing the same. Or think about not doing the same. That's okay, that's up to you. So in the end, this is how you end up. This is the architecture with what you end up. You have the front end, which handles the request from either visualization, the Dalmatiner UI, Grafana, your internal stuff, or any other system that queries it. And the query engine reads from DalmatinerDB the metrics and from Postgres the indexes. Works well. If you produce data, you can use Tachyon, which is a system I built for the cloud, or you can use a Dalmatiner proxy, which is a translator, and they will store it in these two databases. It works. So now I want to show off. And we'll actually ruffle off one of those wonderful Dalmatiner suits, because it didn't fit me, to the person with the best guess. I'm talking about performance. So this I can't ruffle on this because he gave it away. We did performance benchmarks on a system with this spec: 16 cores, 110 gigabytes of memory, and 10 terabytes of disk. And it turns out that you can get a 2.5 to 3.5 million metrics written every second on a single box. The next best system, which is Prometheus, advertises very proudly 800,000 metrics a second. That's an order of magnitude difference. And this is really nice, especially considering it's written in a really slow language. Because Erlang is slow. And here you see it is really slow. Only 3.5 million metrics a second. Damn us, I wish I would have written it in Go. And thanks to the Riak Core architecture, it scales up pretty much in a linear fashion. That is thanks to Basho and not thanks to me. Because adding a new node, it gets distributed, it writes to the new node, and it just goes up. 2 nodes will do nearly double that. 3 nodes will do nearly triple that. So this is for write performance, and now we go to read performance. And now I will take guesses about the 99th percentile read performance for a query querying. Let's take the 8-host query because it's interesting. You query 8 hosts over the last 12 hours and aggregate it by 1 minute precision. So anyone wants to take a guess how long that takes? If you're the only one, you get a free onesie. No one wants to. Okay, if I take the onesie off the table, who is willing to guess? No one. You are all horrible people. I will randomly pick someone of you to give them a onesie if you don't guess. It doesn't work. You're shameless. Okay, for a single host, we are at 13 milliseconds as a minimum, 14 milliseconds as a mean, 16 milliseconds at a 95th percentile, and 18 milliseconds at a 99th percentile with 21 as a max. If you look at that, not only is the time really small, but also it is really tightly packed. The difference between the minimum and the maximum is just 10 milliseconds. If you look at the other systems, the minimum and the maximum are orders of magnitude apart, which is thanks to Erlang's wonderful concurrency and the streaming query engine. Because you can do the computation in steps and don't have these outliners. While one is still waiting, the other one can already work. And the blue ones are the winners. And as you can see, even beating InfluxDB, which is written in Go and does not need to go over the network to fetch the data, we are outperforming them. The same picture paints if you look at 8 hosts. Or at 1 day, all the hosts, which were 10, over 1 day. You have a very tightly packed, very fast query response. Okay, this is me showing off. Now, I wrote a blog post this morning in the plane because I did a lot of benchmarking. It's called The Lies We Tell. If you want to know about all the lies and benchmarking I discovered and did myself, because I'm a horrible person too, then you can go there and read it and say something to it and know why all these numbers really doesn't matter and I'm just showing off. Okay, that's it. Try DalmatinerDB if you need a time series database, or Project Fifo if you want to run a cloud, or get hired by them. They are really nice people. No, they're not nice people. They're good people. Any questions? Am I allowed to do that, or do you want to do that?
You're allowed to do that.
Yes. So the question is, do you store the dimensions with the metric associated at a time or at all times? The answer is yes. The Dalmatiner dimension system is inspired by ideas in Metrics 2.0. So the idea of Metrics 2.0 is that you have two kinds of dimensions. Dimensions which are part of the metric identity. Those dimensions do not change. They are hard-coded. If one of the identity metrics changes, then it's a different metric. The other are the metadata metrics. They can change without actually affecting the identity of the metrics, but they cannot change. They can change, but you will always read the same metadata at all times. So, like, you could have a metadata metric host up or down, which would give you the last written state of this metadata, not the state at that time. If you want the state at that time, you encode it in your own metric. I haven't looked at the metrics 2.0 in OpenTSDB because when I tried it, they didn't exist. Yeah.
What's your current bottleneck for the query engine? What's your current bottleneck for the query engine?
The question is, what's your current bottleneck for the query engine? It's my stupidity, followed by just the raw amount of data. It's pretty much, it depends on the size of the query. It's either CPU or network bound.